transition in an open quasi-periodic ladder. So the study of open quantum system is important because realistic quantum systems are always connected to their environment, and this environmental interaction lead to the decoherence and dissipation. So one of the well studied method is the Lindblad-Master equation approach, which is given by this one. Here rho is the density of the system and L is the Liouvillean and Lm are the Bath operators. And the coherent dynamics is governed by the system Hamiltonian, and the dissipative dynamics is governed by the Lindblad operators Lm. So the eigenspectrum of the Liouvillean essentially determine the relaxation dynamics of an open quantum system, and this is the eigenspectrum of the Liouvillean, where the zero eigenvalue gives you the steady state, which is called the non-equilibrium steady state, and the imaginary eigenvalue is the oscillating coherence. And if both the real and the imaginary eigenvalue are non-zero, then the decay modes are oscillates with its amplitude decays exponentially, and here G is the Liouvillean gap, which determines the relaxation time. So another way to study this system is the effective non-Hermitian Hamiltonian, where A0 is the system Hamiltonian and this Lm part is the dissipation part. Basically this non-Hermitian system shows the several exotic phenomena like the Pt symmetric phase transition through the exceptional points where the eigenvalues and eigenvector coalesces, and the famous non-Hermitian skin effect where the eigen functions localizes at the boundaries, and also the energy spectrum depends strongly on the boundary condition, like under periodic boundary condition it shows the complex energy eigenspectrum, and under open boundary condition it shows real spectrum up to certain dissipation value. So the motivation behind this work is basically we know that in low dimensional systems with uncorrelated site potential the eigenstates are exponentially localized. This the and since the critical disorder strength is 0, here one cannot get the mixed phase zone and mobility edge, and hence there is no metal to insulator transition. But in 3-dimensional systems one can get the mobility edge or the mixed phase zone. However, in low dimensional systems, the low dimensional quasi-periodic system, they behaves differently, like the famous Aubrey and the Harper model, where the transition point has a non-zero value, below which all the eigenstates are delocalized, and after which all the eigenstates are localized. But since the WC is constant and it does not depend on energy, so here also we cannot get the mobility edge, and to get the mobility edge one needs to consider the long range hopping and the dimerized hopping. So the question is that can dissipation modify the localization transition in low dimensional systems, or can we get the mobility edge in 1D system in presence of dissipation? For that we have studied our system using the third quantization approach, which gives the explicit solution of the Master equation, describe the dynamics of open quantum system, provided your Hamiltonian should be quadratic and also the Bath operators should be linear. So from the Master equation we write your Hamiltonian and Bath matrices in Majorana fermionic basis, which follow this anti-commutation relation, and after doing some algebra you can get this you can write the Liouvillean in bilinear form, and this Liouvillean can be described in even and odd parity subspaces, but our observable contain an only even number of Majorana fermions. Since so we can consider even or odd any one of the subspaces. So we will end up with a structure matrix which has a dimension 4n cross 4n. So once you consider the open quantum system with dissipation, your dimension was like n square cross n square. So from there we ended with 4n cross 4n dimension matrix, and from here the different matrices are given by this. Here the important matrix is the damping matrix, which has dimension n cross n, sorry 2n cross 2n, and this Bath matrix you can calculate the Bath matrices from the Lindblad Bath operator. So once you get your Bath matrix, you can construct this damping matrix, and you will ended up with a Liouvillean in diagonal form in normal master modes with the rapidities beta j, which is the eigenvalues of this damping matrix. So instead of studying the full eigenspectrum of the Liouvillean, you can only study the eigenspectrum of the damping matrix, which will give you the same information, and there will be non-equilibrium steady state if and only if all the rapidities have strictly positive real parts. Okay, so here this is our model. We take a two standard ladder for two dissipation configuration. For the first one, we consider the gain and loss in every side, and for the second one, we take it for alternate side. This is the Hamiltonian of the system, and here we take the potential as the quasi-periodic one, like the Aubrey-Harper model, where B is the irrational number, and for the dissipation at each side, the bath operators are like this, and for alternate side, the bath operators are this, and here gamma g or gamma L are the strength of the gain and loss. So then I transform my Hamiltonian in Markov harmonic representation and also the bath matrices, and from this relation I have calculated the so I am quickly wrapping up. Okay, bath matrices, and once we calculate the bath matrices, then we calculate the damping matrix X. So once we get the damping matrix S, I can calculate the IPR and NPR and study the localization transition. So this is the dissipation at each side. Here we plot the average values of IPR for three different dissipation condition. This is the balanced one where gamma g and gamma L is equal to 1, and here we increase the imbalance. So for the first case, there is no mobility as for the no mixed phase zone, and this is the balanced one. As we increases the imbalance, the mixed phase zone appears, and its width increases with increasing this imbalance.
So this is the IPR of what?
Inverse participation ratio by calculating the eigenfunction of the damping matrix.
Of the damping.
Yeah, that X. Okay, then this is the average value IPR as a function of disorder strength. Here we can see the for the resolution. If you increase the gamma L, the transition point from the delocalized to the mixed phase zone moves toward the higher disorder value, and this is the phase diagram with gamma L and V, that it shows three different phases. This one is the delocalized, mixed, and the localized one, and here we plot in color bar. This is NPR average, and this is for the alternate side. Here we get that for the balanced condition also we get a mixed phase zone, and also here the with increases with increasing the imbalance, and here also we get the similar result like the previous one, and this phase diagram shows that the transition point from the mixed phase to the localized phase moves toward the lower disorder value as we increasing the gamma L. And since we have considered the ladder geometry, so it is essential to check the response with respect to lambda and V. Lambda is the interstrand hopping. So when interstrand hopping is less, the effect of dissipation is high. That's why we get a mixed phase zone in lower disorder value. So to conclude, the dissipation induces a complex phase diagram like the extended, mixed, and localized regime, and the most important thing that we no need to consider the hopping, higher order hopping or the quasi-periodic potential, engineering the quasi-periodic potential, and the mixed phase zone we can tune by varying the dissipation strength, and for the alternate side dissipation we get the mixed phase zone even in the balanced condition. So with that I want to thank you for listening.
So is the damping matrix submission, does it have real eigenvalues or?
No, it can have real or imaginary eigenvalue.
So then it would have different right eigenstates and left eigenstates.
Yes.
So which ones are you taking here?
Here I have taken the right one because for localization study it does not affect. I have checked with that.
So this is like the H effective in Lindblad, or how do I?
No, this is not the H effective case. I consider the full Lindblad master equation, then do the algebra like third quantization method, then I study the eigenspectrum of the matrix.
Just one more question we can have.
Okay.
So if this jump operator is not linear in fermionic operator, so
Okay, then this formalism will not work.
how? So in that case, one cannot extract this damping matrix.
No. Then you have to deal with that L square cross L square dimension. Then you cannot reduce. This formalism is only applicable only if the quadratic and the linear.
So you are not seeing any mobility in this equation.
Mobility edge.
You are not seeing in
Yeah, there is mixed phase zone, na. So
but mobility in there should be energies.
yeah, the boundary depends on the energy. You can see. But here I have not studied the expression of this mobility edge or like that. V is the disorder strength, quasi-periodic disorder strength.
Okay, so for mobility as there should be energies separating localized.
Yeah. So this is your mixed phase zone. So this is your delocalized zone. So this boundary depends on the disorder strength.
Okay, I think next time should find
Okay.
out for a nice job and move on to the next slide.
Yes, first of all, I would like to thank the organizers for giving me this opportunity to talk about my work, and also I like to thank my previous speakers to introducing this model, and especially Professor Sengupta to talk about this model and all. And also I acknowledge the funding from NRF. So to start, so there, as you can see, there are a lot of terms: fate of thermalization, pair two-tone periodically different system. So before going to two-tone periodically different system, I will start with the single-tone. What does it mean? I think you have all heard about these things, and you all know about this. So if you consider a typical quantum system, and if you coinch it, you will see that this thing will go to thermalization. I mean, it will give the long time state will be given by the ETH, but that's for a closed system. But if you drive the system from externally and you break the energy conservation, and what will happen is that in that case your Hamiltonian with a parameter lambda, you can periodically tune it such that the Hamiltonian becomes time periodic in time, and in that case you can write the time evolving operator in such form where HF is your Floquet Hamiltonian. This is for HF is a time ordered integral of your Hamiltonian, and it might seems very easy and very closed form looking expression, but it's not easy to get this Floquet Hamiltonian. But in some cases you can get an approximation which is given by this Magnus expansion, and as it turns out that you can get some orders of this Hamiltonian. For example, first order is given by this this integral, this first order is given by this nested commutators and so on. And as it turns out that in the large frequency regime, there is a summation which actually converges, and in that case you can get some emergent.
Converges
Yeah, the large frequency.
in general.
No, not in general. For a two body or single body in that case. Like that's not a general statement. But what I'm saying is that in that case you can get some emergent symmetries. But for a generic many-body system, you'll see that this summation is divergent, and what happens in that case, in the long time limit, if you drive continuously, you'll see that this entanglement will increase, and as a result, the long time will be it will be completely featureless thermalization. This is called the Floquet heating. Okay. But you can actually restrict this infinite temperature heating by introducing disorder, which is many-body localization. Also, there are some. I mean, in some cases, there is something called prethermal regime. Due to the emergent symmetries, if you truncate the Magnus expansion to some terms, you will find that there is a emergent symmetries will come, and due to that thing, you will get a prethermal regime where before going to the infinite temperature state, there is a plateau where you can see that some interesting behavior will come, and this has been observed before, and in terms of calculating entanglement entropy and all. Here in this case, I will discuss about the PXP model, and it was already observed that in the flat melt limit, which I think you have heard in the talk in the morning, that in the flat melt limit there is a prethermal regime, right? So this model is given by this Hamiltonian, where we have this this term which is a transverse, these two terms are lambda 1 and lambda 2, these are the two parameters. Here we are instead of one tuning, we are tuning these two parameters and they have two different periodic frequencies. Okay. So this Hamiltonian as already have introduced that there are this, it restricts this to consecutive spin up states. So basically only spin flipping is possible only if you have two nearest neighbor down spins. Okay. And in this case this lambda and lambda 2 they are all periodic, but they have two different time periods which is T1 by omega 1 and omega 2, where omega 2 and omega 1 they are related by this ratio which is nu. Where is nu? This nu is the nu, depending on the protocol it can be integer and yeah. So these are the two different protocols, the cosine for the square wave. As you can see there are this omega and omega 2. So this lambda 0 is the red one is the for this one frequency, and the lambda 2 is the other frequency. As you can see there are two different frequencies. Now so we have seen that this Prithamar regime can actually restrict this infinite temperature heating. Also there is something called measurement induced phase transition, where if you consider the same closed quantum system and if you let it evolve, you see that entanglement increases. But if you introduce measurements at different times, you will see that entanglement will decrease. Okay. And there has been a lot of studies in this direction in the previous decade in terms of circuits, even in Hamiltonian. So here you can see that these are the 2 qubit circuits, and also these are the measurements you are doing at different sites. So as a function of this measurement strength, you will see that for a different measurement strength below a critical value, there is entangling phase, which is the volume law phase, where you see that all the sites are coupled with all the other sites in the system, and this is volume law entanglement. And if you increase this measurement strength, you will see that the long time and the entanglement decreases, and this phase is low entangled phase, which is known as low area law, which only the boundary terms are contributing. And this transition as a function of measurement is known as measurement induced transition. And so here what I will do, so I will do this, I will couple these two things. Okay. So now what I will do, so in this case I will consider this Fouquet unitaries, where all my sites are evolving with time period t, and then we are also making measurement at stroboscopic time. Okay. So these red dots are given by measurements, which is done with a strength p and with probability given by this bond probability. So what I am doing is that I have an initial state which is a all down state. We can consider global all down state, and then we are drawing a random number from this distribution, because you know when you are measuring during the evolution, there is these events are rare events, and you can actually get them from a Poissonian distribution. So you have to then once you get this waiting time, you evolve this up to this time by this unitary, which you have already obtained for the periodic different systems, and then 3 minutes. Yeah, sure. I'll just finish. So and then you will get after once you evolve up to this up to time tau m, then you make the measurements, and measurements are done with these probabilities. Okay. So now I will discuss the results and the conclusion. So in this case, as the PXC model already had been introduced, so there is the Prithamar regime. So in this case, let's first consider without the measurement. Okay, this is without any measurement. So in this case, for what we have already seen, that there is a Prithamar regime. So in this axis we are plotting the entanglement entropy, half chain entanglement entropy, and with a function of W0. So W0 is one of the parameter which governs the model whether it is a flat band regime. When W0 is 0, it is a flat band regime, and when you increase the W0, it is in the Prithamar regime. So these are given by these values of the entanglement, and this black dashed line represents the singleton. So if you are driving the model with a singleton frequency, you know that this system will heat up, and then you have a thermal behavior here. But with a two-tone, you are seeing that this is a Prithamar regime, and with increasing W0, this increases. So this has already been produced in the literature, and these are the singleton result. This is the Prithamar result. Now let's add the measurements. So what we are having is that once we add the measurements, so this is when you don't have the measurement, p equals to 0. So then we have this. These are the Prithamar behavior. Now as soon as we add the measurements, you don't see this Prithamar regime there. Now you are seeing a volume regime. Okay. And it's suddenly the entanglement is increasing, and then as you increase the measurement strength more, you start to see that entanglement is growing and they are entering into the area law phase. But there is a difference, so depending on the value of W0. So once you are in this value, so when W0 is within this Prythamer regime, you are seeing that there is a crossover. So once you increase the measurement strength, you see that the volume law continuously decays to this area law. There is no transition. But as you have a W0 is larger, you see that there is a transition from volume law to area law. Okay. So this transition has to be more characterized with the different system sizes and all, and these are very initial stages of results. But yeah, as we study this, and this will be more clearer. But this is the overall picture, and this has been studied for 3 different system sizes, and these are the results. Yeah, so that's the conclusion. Thanks.
So in one question I'll ask few things. What is the form of LJ? What is that dotted line?
Cluster bomb.
What is the form of LJ? What is that dotted line?
So LJ,
And this black line that you say is the single tone. If you had single tone, then it is. I mean, to me it seems that the entanglement entropy would have no effect of these embedded measurements. So I just want to understand that you're driving your system n number of times, and then at the end you're putting measurement. So anyway, you drove this n number of times, and then you put measurement. So it seems that if for the single tone, P has no effect. So
no, here I just added this line for reference, so there is no measurement there.
Okay, so there is so it was supposed to be like this, but for two tone,
Yeah.
You have done this.
Yes,
so
yes.
For single tone also, you expect. That
Yeah, that's true.
You will get some
Yeah.
area law to volume law
Yeah.
transition. What is this dotted line?
So this dotted line, so there this phase diagram has to be more quantified in more detail. So this thing is like crossover, not a transition. Just to make from a volume law to area law, there is no transition there. But here what I am seeing is there is a transition. So in that case,
So here you see
I think we postpone further
LJ, the
discussion.
form of LJ just last.
form is the spin up operator. You just operate the spin of 1 plus sigma g by 2. So that's a Pauli operator. You just operate. Yeah.
Thank you very much.
Yeah. Thanks.